Hello everyone, I'm Vineet Tamija, and along with my colleagues Neil and Rakesh, we have worked on data-driven car following model. According to Statistics Canada, 80% of commuters choose to travel to work via a car, and that sums up to around 22 days that you spend on the road traveling to work, which does not include the time that you spend with your families on your trips or grocery shopping. With this much time spent on the road, you would assume that the roads are safe. That's no wonder future is for autonomous vehicles. When everything in a future perfect world is autonomous vehicle, they will be able to interact with each other. They will know which car is where at what time and what's the speed. But unless that time comes, currently an autonomous vehicle needs to run on the road along with a human driven vehicle. How will a autonomous vehicle identify how a human is going to interact? That is something which is made possible by car following models, which are able to predict based upon a car combination where the vehicles are going to be, what the outcome is going to be, what speed they are going to be in. That is something which will be predicted via a car following model, which have existed surprisingly since 1981. But what we have chosen to do is create a data driven car following model, because the existing car following models always have worked on some assumptions which do not work on all of the scenarios, but a data driven model will be able to mimic a human behavior as close as possible. Before looking at the results, let's quickly review a few of the literature which will help us understand it better. Velocity is the speed of the vehicle with which it is running on the road. Position is the distance it has traveled. Acceleration is the change in velocity based upon some particular time. And jerk is the change in acceleration based upon some particular time. We trained three different models, which are random forest, KNN, and CNN, for various reaction time. The question comes, what's a reaction time? The time it takes for you to react for a change in the road. Suppose the lead vehicle brakes. When he brakes, you analyze that information in your brain and you apply the brakes yourself. Or you may not if the distance is too much. But the time it takes for you to react is the reaction time. We trained our models based upon zero point 0.1, zero point 0.2, 0.35, 1, 2, and 4 seconds of reaction time. We have created this demo app which is going to show you the trajectories or the predictions that we or our models made based versus the actual subject vehicle information for various combinations. There were three combinations that we trained: car, heavy vehicle car, and car. For various vehicle informations, we picked up three random vehicles combination for each vehicle combination out there and predicted or displayed the various information that we are going to review. Let's look at the first one, which is acceleration, which we are predicting, and based upon the prediction of acceleration we are calculating the rest. If you look at this particular plot, the first one, what it is showing, it is showing the acceleration of that vehicle, the subject vehicle, for the total duration of 50 seconds of car following. The blacks are the actuals, blue is the random forest. Random forest is able to meet most of the oscillations here. When it is going up, the predictions are going up. When it is going down, the predictions are going down. Same thing for KNN. It is also able to meet most of the oscillations out there. And if you look at CNN, not so much. Based upon the acceleration that we received, we calculated the velocity. And looking at the velocity predictions for the entire time duration, we can see for all together in this one plot or one by one starting the next. CNN is able to meet most of the oscillations, but not exactly. It is smooth, whereas the actual values were not so smooth. The second one, if you see here, the blue RF, it is able to meet most of the velocity predictions. we are able to predict correctly the actual velocity out there. Same thing for KNN. And how are we predicting? We only receive the very first value of the subject vehicle for which we are predicting. You find out the first value, and based upon that value, you keep on going in the time series and keep on predicting. And the third thing that we have to calculate is the spacing, which is the distance between the two vehicles, which is ideally the criteria based upon which a vehicle will either speed up or brake. All four together, similar manner, 50 seconds of car following. You can see that CNN is doing the best for this particular example. CNN is meeting most of the spacing. RF did a little bit not better, and KNN did the worst in this particular example. Let's look at the jerk. Jerk is the sudden acceleration change that you have, which is oscillations are still met. Even in KNN oscillations are met, in CNN the oscillations are not met. So based upon all the oscillations that we see, or we could see for someone else as well, Random Forest, KNN did much better, met all the oscillations, CNN not so much. Or you could see all of them together for this particular vehicle. How did we come up to these results? We picked up the NJSIM dataset, which is a dataset provided by US Transportation. It calculated, it has 11.8 million rows out there for a preciseness of 0.1 second for three vehicle combinations, which is car, motorcycle, heavy vehicle, and they calculated this information on 4 highways with 15 minutes video each. 75% of that data existed for US 101 or I-80. That is what we have concentrated on at this time. I-80 runs from east to west, and they put up 7 cameras for 15 minutes each video. They calculated or picked up the information from those videos and created an Excel with a preciseness of 0.1 second. Each row or values of velocity, acceleration, distance, length is put in that data set at after every 0.1 second in a time series. The US 101 runs from north to south, same thing, 15 minutes videos, 3 videos for 8 cameras. But as everybody knows, no data can be entirely clean. We had to remove anything which had lane 4 and above, because most of them are highway exits or ramps. Any vehicle which will take more than 10 seconds to catch up to the following or the lead vehicle, we have removed. Any pair of following which is less than 30 seconds, we have not kept, and any trajectory for a vehicle which is about to overtake, we have not kept. We did a few transformations as well. We converted everything from feet to metric. We converted everything from front to front information to front to rear information, because any vehicle always looks at the rear bumper rather than the front, but we were given the front to front vehicle information. We have kept 5 common features for all of the models, which are the distance between the vehicles, what type of vehicle there are, the vehicle class, the difference between the velocity of the current vehicle and the lead vehicle, and the velocity of your current vehicle, which will be used to predict the acceleration. All 3 models have been put up with 80-10-10 train test split. The Random Forest has 30 estimators, KNN had 5 neighbors, and Neural had 3 blocks of Con 1D batch normalization dropouts, followed by 3 dense layers with a combination of activators such as TANH, sigmoid, and LU. The results trajectories you have already seen are better or best for KNN if compared with both RF and CNN. But the R-square and RMSEs come up and show that CNN is better, which isn't the case. The oscillations do not match at all for CNN, but if you see, CNN has the least R-square, KNN had the worst. KNN has the worst for jerk, acceleration, spacing, and velocity. Best ones, CNN. Same thing for RMSE. KNN shows that it has the most error, for jerk, acceleration, spacing, and velocity. And CNN had the best, but that is not the case. Because the accuracy errors are not matching the trajectories that we saw, we are in future going to use dynamic time warping to verify the accuracy, which is something which helps us identify or predict the accuracy and calculate it for a time series data, which we have right now. We are going to retrain the model for all four data sets or highways they had done, Lancashire and Peachtree as well. We were not able to use 150 regressors, which showed us the best results because of our system limitations, but we will probably put it onto a Docker and server where we will be able to use it for 150 regressors and train it as well, and create the prod app rather than the demo, which will be able to use our Excel with the current input only and predict the entire trajectory of the vehicle that we want to calculate. Thank you.